Welcome to lecture number 8 in Neutron 302. Last lecture we talked a bit about scattering events. We took all of our expressions that helped us predict the kinetic energy of the products as a function of the energy of that incoming projectile. We took all those expressions, we simplified them because we restricted ourselves to looking at just neutrons and scattering events, elastic scattering. And so we found some greatly simplified expressions there that helped us understand the ability that different targets have to slow down a neutron. We want to go from a high energy down to a thermal levels of those neutrons. And then we ended off the lecture last time talking a bit about cross sections. The cross-section that we dealt with last lecture was what's called the microscopic cross-section. Today we'll extend that. We'll talk about the reaction rate, revisit that a bit, and then relate this microscopic cross-section to what's called a macroscopic cross-section, and revisit some of the sources of the nuclear data online and make sure that we understand how to use those. So today we'll talk about the relationship between the neutron flux, the neutron rate, reaction rate, and then we're going to weave in this macroscopic cross-section into that discussion. And so if you look at the neutron flux, and just as a reminder, my units here are going to be neutrons per area per second. This is what's called a scalar flux, and we'll talk about what that means here in just a minute. But my neutron rate is just going to be neutrons per second. And my reaction rate is going to be reactions per second. And really reactions is a number, it's an integer. Neutrons is a number, that's an integer. And it's the cross-section that converts it from one to the other. We don't keep those units in any of the parameters or calculations. But in reality, that's what the cross-section is doing. It's converting it from neutrons and atoms, so that we've got three quantities that are just integer values. They're just numbers. They're unitless, but they're not all equal. We've got the target, which has some atom density, so we got the number of atoms there. We got the total number of neutrons that we're shooting at this target. And then we have the number of reactions, which is going to be a small fraction of the potential. The potential is all the atoms in that lattice, all the atoms in that target could go under some reaction, and we're going to be some very small fraction of that. But even though it has units, you can think of the cross section as a probability-like metric, and indeed we can relate it back to the probability like we did last lecture. So when we take this neutron flux, it's defined. It's going to be dependent on space. It's going to be dependent on time, as you see the R and the T. But it's going to be defined in a formal sense as looking at some target. So looking at some target area, we'll call that delta A, and we look at all the neutrons being bombarded in that area, and if we take the limit as that goes to 0, then that's going to be what we're calling this neutron flux, this scalar flux. So the correct label here is a scalar flux. And in words, what we would define this as is this is the total rate at which neutrons are passing through some unit area. And so we label this with the word flux, but the fact that we have the word scalar before that is something that's important for us to understand. So when we deal with flux terms in other disciplines, normally we're looking at the amount of stuff crossing this unit area in a direction that's perpendicular to that area. And so especially when you get into fluids and heat transfer, we talk about a mass flux or a heat flux. That's going to be the amount of heat that's traveling or the amount of mass that's traveling through a unit area and perpendicular to that area. And so that velocity, the mass velocity there, and the heat, these are vectors. In this case, the neutrons, even though we could think of them as having a velocity vector tied to them, we don't really care about that. We just want to know how many neutrons are passing through this area. We don't care what direction they're coming through. We just want to know how many neutrons we have every second in this area. Also think of it in terms of a unit volume. And so that's the definition. That's the difference between calling something a parameter or a metric a flux versus a scalar flux. In this case, we don't really care about which direction it's coming from, just as long as it's traveling through that area delta A. And so that's the definition here, is the total rate at which neutrons pass through a unit area. There's no stipulations there on which direction it's traveling. And so we could also define this then in terms of our beam velocity. Let me reorder that. In terms of our beam density and our beam velocity. So this will have units of length per time, and this one here is our beam density. This is a review from last lecture. This will be neutrons per volume. And the beam density is also going to be a function, technically, of both space and time, just like that neutron flux is. And the beam speed, we should note that it's not necessarily going to be one speed for all neutrons. You might have different neutrons at different speeds, and even in a very controlled experiment, you might have 2 or 3 different neutron beams coming in, and different speeds, different energy levels for each of those beams. And so if we did have multiple beams, the way that we would add these together is just to sum up all of the products of the beam speed and beam density. So if multiple beams, then our scalar flux, our neutron scalar flux, is just going to be the sum of all those. We got one beam density at one speed, and a second one at a second speed, and a third one at a third speed, and so on and so forth. So each of these products here has a scalar contribution to the overall scalar flux. And we can treat these independently, and then we just add them together. But the reality is that all these parameters are going to be very spatially dependent, like in a core. And as we talked about last time, the speed of those neutrons is going to change as a function of time, and how many times they collide with whatever moderator we happen to have in the reactor design. And we want to bring those down to room temperature, and we're often going to look at this speed of 2,200 meters per second, and that's basically our room temperature speed. Oops. So by room temperature, if we say that our temperature is 293.15 K, then our kinetic energy is just the Boltzmann constant times that temperature, and that's going to be 0.0253 eV. And so when you see this in a table, then what we're assuming is that neutron now has been thermalized. The energy of that neutron has been brought down to a speed or to a kinetic energy that corresponds to a room temperature, basically. And so we're going to look up different data, and in today's lecture we'll focus on that energy level. Let's go do a couple of examples. As we go to our first example, in this example we have some experimenter that is designing a neutron beam, and there's going to be 5 different beams, and they're all converging on a single target at the center of a circle. 4 of those beams have a neutron production rate of 10 to the 4th neutrons per second, and the 5th one has a higher production rate, 10 times higher, 10 to the 5th. And we want to, first we're going to assume that all neutrons are at the same speed, so 100 eV. And we want to know what the one speed flux of neutrons if all beams focus to this small area, 0.1 millimeters squared. So we'll do that first, and then we want to consider case 2, where the 5th beam, then I can independently tune that to a higher energy, so from 100 eV to 200 eV, or 200 eV. The other 4 stay at 100 eV, and then we ask ourselves, well, what does that even mean to say what is the one speed flux on target? So we'll first do case 1. In case 1, our flux then is just going to be equal to, it's the sum of all those products. And so we've got 4 of the 10 to the 4th neutrons per second. And then we got 1 of the 10 to the 5th neutrons per second. And we want to multiply that by, it's the same area there. And that is, it's going to be 10 to the minus 3 centimeters cubed. That's our area right there. 0.1 millimeters cubed is the same thing as 10 to the minus 3 centimeters cubed. And we do this calculation, we get 1.4 times 10 to the 8th neutrons per centimeter squared second. And that is our one speed neutron flux for this case 1. For case 2, we take the 5th beam and we're going to increase its energy level. And actually, let's do this. Let's just make a note here. Beam 5 is changed to 200 eV. But it's important to note that this here, this is my neutron rate, neutrons per second. Just because we increase the energy, so increase the speed of that 5th one, it didn't say that we also increase that n dot. And if we're not increasing the n dot, if we're not increasing the number of neutrons every second, yeah, they might be coming in higher, but they're not coming in more often. They're coming in at the same rate, 10 to the 5th neutrons per second. And that's really all that we care about. And since that didn't change, this neutron flux is going to be the same as what we found in that first case, neutrons per centimeter squared per second. But it's important, I mean, this note here, when we talk about one speed, what's the one speed flux on target, it doesn't make sense to even talk about that in this case too, because we have 2 speeds. And so you would typically consider those independent of each other and look at the impact of this lower speed, then look at the impact of the higher speed, and then discuss those impacts independent of each other. And so when you have more than one speed, there's no reason to talk about what is the one speed. So the conclusion here is this is not a one speed flux. Okay, we look at our second example now. We want to find the speed and the number density of neutrons of energy 1.5 MeV in a flux of 7 times 10 to the 13 centimeters squared per centimeter squared second. So this will be our phi here. Oops. And this here is our kinetic energy. And so with this kinetic energy, we can find the beam speed. Let's do that first. So kinetic energy is going to be 1/2 mv squared, which tells us that V is going to be 2 times the kinetic energy divided by mass, square root. And so we are going to then just use this information. We have 2 times 1.5 MeV divided by the mass, which is a mass of a neutron, 1.008665 AMU. And I can convert that, I need to convert that to consistent units. I need to convert the MeV to joules and the AMU to kilograms, and then I take the square root of that. I should have units of meters per second, or I convert it to centimeters per second, and that's what we'll do here. So velocity is 1.69 times 10 to the 9th centimeters per second. And you say, well, that sounds awfully fast, and it is, but it's only about 6% of the speed of light. So that tells us our beam speed. We found our beam speed here. And now we need to find the number density. So we'll just use this expression that our flux is going to be equal to that speed times the beam density. So N is just the flux divided by the beam speed. And the flux is given here 7 times 10 to the 13th centimeters squared per second, and divided by the velocity, and so that's going to be 1.69 times 10 to the 9th centimeters per second. My seconds cancel out, and I'm left with the beam density, which should be number of neutrons per unit volume, and that's what we get. Do this calculation, and I get my beam density is going to be equal to 4.14 times 10 to the 4th neutrons per centimeter cubed. Okay, so now if we go back to our lecture, and if we recall from last lecture this expression for reaction rate, we've got the reaction rate, which is reactions per second. We've got the beam density, we've got the beam speed, we've got the cross-sectional area, we've got the microscopic cross-section, the sigma. We've got N, which is the atom density of the target, and then we've got this delta X, which is the thickness of that of the target. And as a reminder, the probability of a reaction is going to be equal to sigma times N times delta X. And that sigma, the product of sigma and N, so our cross-section, our microscopic cross-section, and our atom density, these two are always going to be together. And they're both material properties. In other words, in order to find sigma, I need to ask myself, well, what is the cross-section of this target, of whatever the isotope is? And to find N, I need to ask myself, well, what is the material of the target? And so the sigma is going to be dependent on the energy of the neutron as well, but and N is going to be independent of that. But they both require me to look up information about the isotope. And so they both depend on the nuclear makeup of the target. And because of that, we lump them together quite often, or since they're always together, we lump them together, and this is going to be our what's called the macroscopic cross section. We take the sigma, which is really some measure of a single atom of that isotope and a neutron, and its probability of interacting with that neutron. So we would take sigma, which is a probability-like metric that is tied to a single atom and a single neutron, and how likely is it to interact. And then we take n, which is the number of atoms we have in a given volume. And so that takes it from the microscopic world of a single atom and the possibility of interacting there to this bigger target by virtue of multiplying that by n. And so we call this the macroscopic cross-section. It's going to have units of 1 per meter, 1 over meter or 1 over centimeter. And so our probability is going to be expressed as that sigma, our macroscopic cross-section, multiplied by the thickness of our target. And when we have different types of interactions, then we express those possibilities as cross-sections of those different types of interactions. So we have our total cross-section, this sigma t, either in the macroscopic sense, the top equation, or the microscopic sense, the bottom equation. And each of these are going to be split up into two families of interactions. Same thing for my microscopic. And these subscripts here, this is my total, this is my scattering, and this is my absorption. And each one of those two has some subcategories of what happens after that. So the scattering could be elastic or inelastic. So we'll come here, we'll say sigma s, so that scattering cross-section is going to be comprised of an elastic scattering, where I don't have any change in mass, it's just the momentum's conserved, the mass is conserved. Or I could have sigma I, which is going to be my inelastic. I have a neutron coming out, but I gave some of the energy to the nucleus, and it becomes in an excited state. And then sigma A, this absorption, is going to be comprised of, typically call this gamma, which is going to be that we just capture the neutron. Another option here is going to be fission, or a bunch of other ones. So there's primarily just two for the scattering, and there's two main ones that we're going to focus on for the absorption. But the reality is there's quite a few in that category. But the take-home message here is that you would find your total cross-section either in a microscopic or a macroscopic sense as just the sum of all the individual components. And so if you're asked to find out, well, what's of all the interactions that take place, what percentage of them would I expect to be fission? Well, you just take the fission cross-section and you divide that by the total cross-section, and there's your ratio. But again, that's of all the interactions that are going to take place, how many of them would be this or how many of them would be that. And so we'll look at this in a little bit more detail in the next example, and then we'll visit some of the resources again online. So as we go to our third example, we have a neutron beam at 0.0253 eV. We're familiar with what that means now. We have a U-235 target. We want to know what percentage of all the interactions are fission interactions. And so it's just like we were saying before, we need to look up the cross-section for fission of U-235, incoming neutron. We need to look up the total cross-section for U-235, incoming neutron. and the percent of the fission is just going to be a ratio of those two. And so we need to look at this energy level. We need to find out what our cross sections are. So we find our total cross section, we find our fission cross section. This will be in units of Barnes, and the percent of reactions that are fission is just the ratio of those two. So we'll go look that up in just a second, but conceptually that's what we're doing. We just need to know those numbers. We take the ratio of them, and we see how much is due to fission. But let's read the rest of the sentence and just ask ourselves what else are we looking for here, and then we'll go look up those values. So we also want to know what is the macroscopic fission cross-section for a U-235 target. So we're given the density there of U-235, and so we're also given the we're going to look up the fission cross-section, and so this is the second part here. We want to find the macroscopic fission cross-section is just going to be that microscopic cross-section multiplied by the number density of my uranium, which is going to be sigma F multiplied by the density, which is given in, not the density of fission, but the density of the U-235. The density multiplied by, we did this last time, we want to multiply that by Avogadro's number and then divide that by the molecular mass of the U-235. And if you remember the side note that we had on one of the examples last time, then the molecular mass, grams per mole, is the same thing as AMU per molecule. Okay, and then once we do that, we can easily calculate our fission cross-section. And the next thing is asking us if the slab is 1 centimeter thick and the incident neutron beam sends this many neutrons per second, so we've got our n dot. How many fission events are expected each second? So we need to look at the reaction. We can look at the total reaction and multiply it by whatever fraction we get here. Or we could just do this in terms of fission. So we can find the reaction rate for fission events is just going to be equal to the following. And we're going to replace this here. These three together are my n dot. And this here is my sigma. And we're going to use sigma fission because this is fission. And then I've got delta x, which is given in the problem statement as 1 centimeter thick. And so I've got all the information I need there. I just need this fission cross-section, and n dot is given to me. So that's the next part, and then the final part is looking at what the power generated. So now we know how many fission events happen every second. And we are saying that every one of those, we're going to get into more detail on quantifying this later on in the semester, but for now just take it as 200 MeV for every fission event that occurs. And if that is the energy that's released, then what is the power generated? Well, energy per time is power. And so this last part we will just say the power is going to be whatever that reaction rate is that we find from the previous part, and we multiply that by the energy of a single fission event, and that's going to be my 200 MeV. And we should have units of watts by that time. So we have an energy, MeV, per second. So an energy per time is a power. All right, let's spend a little bit of time looking at some of the resources online. We'll go through, I'm going to do this through two different resources. The first one's this Janus, which if you are interested in the software, you can download it for free and install it on your computer. You do need to have Java installed in order for it to work. I'm just going to browse the online database here to access the same data. And then we're going to go to the Korean resources here, and we're going to compare, contrast the two, and look at different steps that we need to take in each of those to get the data that we want. At the end of this, for this problem, we just need to know the cross-section, the fission cross-section, and the total cross-section for U-235, an incoming neutron, at 0.0253 eV. So that's room temperature, the thermal neutron. So in Janus here, we can browse the database, and we want to look at incident neutron data. And these are the different databases. So I generally will just use the most recent or the highest NDEF library. And I want cross sections, and then I just look up our target as uranium. And now I'm going to be able to choose my isotope here, uranium-235. And I want to know the total cross-section. So I'll click on this one, and then I'll click on cross-section. I need to click on this icon here, this open. And I don't have anything shown here, but I haven't selected whether to give it a plot. So if I select plot, you should see here's my cross-section as a function of incident energy. This is in units of MeV. I can also display this in tabular format. And you can see up here I've got two tabs. So I've got the plot, and then I've got the data itself. And the data is comprised of 81 different pages of this many sets of data. But really I just want to scroll down to 0.0253 EV. And so in this case we've got either the -5, -4, 0.0253. So that is my cross-section data in units of Barnes for the total cross-section. So I've got a value of 700.2. Now let's go to the Korean resource and look at the same thing. Go to table of nuclides, come up here and type 235U, and come here. These are my different libraries now here, and so I'll go to that same library, look at my cross-section data, and I want to click on the total cross-section. So I click on the plot, and this plot just appeared down here. And last time we looked at a bunch of different plots together, and I can do that, but I don't really need to do that here. I can look at this, or I can go get the data. And again, I'm looking for, here's my energy in EV, and there's my cross-section in Barnes, and I'm looking for 0.0253, and there it is here. And so I have a slightly different number, which is interesting and maybe alarming. I'm using the same database. This one was 700.24, this one is 700.11. And so we're talking about 1 unit in 7,000 units. And so it's the difference here is minimal. And in reality, none of these numbers are perfect. It's not that I had a neutron exactly at 0.0253 000 EV that I was doing these experiments with. And when one measures the cross-section, it's not that you are measuring it perfectly. And so there's uncertainty on both the X and the Y data points for these plots. And so it's not surprising on the fact that someone would incorporate the uncertainty in a slightly different way. But it's one unit out of 7,000, so a fraction of a percent difference here. So I can take either one of those two, and the bottom line is what you should do whenever doing a problem like this is to cite the source and the data set that you use to look up cross-section. But I did want to show one more resource that I find useful. If I go to this Korean data set again, go back here, and I actually go to the previous version of this table. And it's organized here, just a list of elements, and so I go into uranium, and I go into U-235. And here it's got a bunch of just standard data that most likely you would care about. The percent abundance, naturally it's got half-life data. We'll get into that next chapter. But over here, if you go to N cross-section, and so a lot of what we do as nuclear engineers is we're talking about incoming neutrons, and so cross-section for neutron projectiles. And you see that it gives me values for total cross-section at 0.0253 eV. And then it gives me the same measurement, my total cross-section in units of barns, at a high energy value. So in this case, 14 MeV. And so I can just read this off of here. I can get my elastic scattering cross-section. And by the way, if you take each of these cross-sections that are listed here and you add them up, well, there might be some that are small and not listed, but you should more or less get this value here, which is your total cross-section, because it's just the sum of all possible interactions. And as long as we are listing all possible interactions, then we add them up, we should get the same thing. But that's the number I want, 698.2, and so you see this is more than 1 unit out of 7,000 different, but again, it's still a very small percentage difference. And I find it most easiest to use a resource like this rather than having to print out that array of data and go search for the 0.0253. Now, if I'm using anything other than 0.0253 or 14 MeV, this is of no use to me. But I can still always go to the data there, the table. So I'm going to use these data points. I'm going to use 698.2 for my total cross-section, and then I come down here to my fission cross-section is right here, so 584.4. And so of my total cross-section, 698.2, most of it is due to the fission, and that's why we use U-235, right? You see these are in millibarn. I think one of these might be microbarn somewhere, but no, maybe not. But yeah, so this is 0.5 or 0.04 barn, and this is 0.5 barn, and this is 0.3 barn, and so on. But those are the two numbers I'm going to use for this problem. So I'll use the total cross-section of 698 and a fission cross-section of 584.4. So when I do this calculation, then I get it's 83.7%. And so 83.7% of the interactions that do occur are going to be fission events. And so if that's my neutrons per second, then 83.7% of those are being used for fission. Now, obviously, a fission event is going to generate another neutron, but we're not going to get into that complexity in this lecture. We'll be addressing that later on. So I've got that number, and then here I'm just going to say put in my calculations here. So I've got my 698, or I just want to do my fission, so that's 584.4 barns, and then I know that there's 10 to the minus 24 centimeters squared per barn, and then I'll multiply it by the density, which was given as 19.1 grams per centimeter cubed, and then I'll put the centimeter cubed down here. And then I multiply that by Avogadro's number, 6.02 times 10 to the 23rd. And divide that by my molar mass, which is 235. I can go look this up for you, 235, but it'll be 4 grams per mole. And so my units I've got centimeter squared, get rid of my barns. My grams are gone, and there's a mole up here for my Avogadro's number. And I'm left with just that extra centimeter down there. And so my fission cross-section, if I do this calculation, then I get 28.6 per centimeter. That is my macroscopic fission cross-section. So now I go here, and I'm just going to multiply n dot, which was 10 to the 12th per second, and then I'll multiply it by my macroscopic fission cross-section, 28.61 per centimeter. Oops. And then I need to multiply that by the slab thickness, which is just 1 centimeter. And so in this case, I find that RF is going to be equal to 2.86 times 10 to the 14th fissions per second. So every second that ticks by for all these numbers, then I would expect 2.86 times 10 to the 14th fissions. Now the question of power, I take that reaction rate and multiply it by the 200 MeV. And so this is 286 times 10 to the 14th per second. And I know that there's 200 MeV. And I'll convert that to joules. I got 1.602 times 10 to the negative 13th joules per MeV. And what I have here, my MeVs are gone, and I'm left with joules per second. Joule per second is a watt. And once I run these numbers, then I get that the power is going to be equal to 9165 watts, which is 9.165 kilowatts. So for a slab that is, how thick was it? 1 centimeter thick, I've got almost 10 kilowatts of power. And it might be the question in your mind of how do we know how many reactions are occurring every second if we weren't given any information on the cross-sectional area? Right? We were given the thickness of the slab, but we don't know what the cross-sectional area of the slab is. We don't know the volume of the slab. So how could we ever know how many reactions are happening per second if we don't know the volume? And the answer to that is it's sort of built into this number here. The fact that it's given in units of neutrons per second means that there is an area already factored in there. So yes, your intuition is correct. If you looked at that result and you thought, well, we need to know the volume in order to know how much power is coming from this slab. So you're correct there, but it's built into our neutron rate there. Okay, so that concludes this lecture. We will see you next time for lecture number 9.